anything else.
Yeah, then I'm gonna need to like people with logs to calm down.
Yeah, it's been doing some stuff. People.
So we just do logs.
Should we start? Wait a minute. A little bit more. Yes, we have time. I put in a slide for draft status.
Oh, you did? Okay, great.
This is Matt's be okay like presenting or just giving an update.
Just call into the mic.
Yeah.
Yeah. Okay. Great.
And they're trying to kind of share between two different processes.
All right. All right. Hello, everyone. Welcome to Pair G. I'm Chris. This is Siobhan. Sarah is here. Is she here, actually? I don't think she's here. She's here with us in spirit. I don't know if she's online right now. Next slide, please. This is the Notewell. Assuming you have all seen this before, but just in case you haven't, you can check it out online. But the high-level takeaways are be mindful of the IPR policy as well as the code of conduct. Generally, just be friendly and respectful, and we should have a grand old time here talking about privacy things. Next slide. As an additional reminder, IETF116 does require all active participants in the room to be wearing a mask unless you're actively eating or drinking. Please obey the rules so we don't have to come and talk to you and be awkward about it. Thank you. This is our agenda. Thanks, Matt, for taking notes. We're going to start with a quick update on current drafts in the group and then go into a bunch of presentations on a variety of topics. Before, I guess, jumping into the updates, does anyone have any adjustments or other comments they'd like to make on the agenda as it is? Okay, hearing none. Next slide. These are the drafts that we have active right now. Some of them are being actively developed. Some of them, there are some adopted drafts that are expired. I wanted to quickly see if we can get an update from Matt, who is in the office on the in the room on the IP address privacy considerations one, which is a draft that was adopted. I don't remember exactly when, some time ago. It's gone through a number of updates, but still needs a bit more work. Yeah, if you could, please. Yeah, that mic is fine.
Yeah, Matt Apple, previously Tor. So I haven't actually worked much on this. It's very high on my list. Since the last meeting, we haven't done anything, so I don't recall what the last update was, but I know at that point I had recently talked to the authors about some structural changes in the organization that we were planning on doing. We haven't actually gotten to doing that, but I am optimistic that that is coming soon.
Great, thank you, and don't take this as criticism. We know everyone's super busy, so and there have been some other people I don't see in this room right now have expressed interest in potentially helping with this. I don't know if they've spoken with you, but we can connect offline to
that'd be great.
That out.
I appreciate it.
So thank you, Matt. The other drafts we have, the censorship survey one, has sort of gone quite far along in the process. In IRC review right now, we do need we're tracking down some updates before we move it forward. Did you want to say more?
Yeah, I think it was just a new version was just cut, so I think it's just
great.
we're pretty. I think it's just a quick review, and we should be good to like push it forward.
Great, thank you. And then there's the safe measurement guidance draft, still being actively developed. Unfortunately, I don't see Mallory here or anyone else here who could potentially speak to it as an author. But we're working with them to make sure that continues to move forward. If anyone's interested in working on this topic or contributing to that draft, of course, please reach out to the editors or send comments to the list. Reviews are always welcome. And I believe that's it, unless you want to say anything else.
Yeah, I guess also, I think the chairs think that this draft, this safe measurement draft, is kind of interesting and important given the work happening in the PPM working group. So that's also why I think this would be a useful draft. And I guess the other two drafts, which were the on the generation of transient numeric identifiers and the unfortunate history of transient numeric identifiers, both those drafts have been sent to the RFC editor. So there was some discussion about how we pipeline those with respect to this other draft. So there's some conversation there, but the chairs are working on that. Should be published soonish.
All right, that's it. So on to the presentations. First up, we have Martin to give us a kind of an overview of sorts on IPA, interoperable private attribution. And we have 30 minutes queued up for this. It is, I don't know if that's sufficient, but we'll find out.
It's easier to make it work when I turn the microphone on. Hi.
We'll pull them up. Yeah, just one
Yeah.
moment.
I should have put that a new deck is being shared in my presentation. Anyway, Martin Thompson. I'm here to talk about attribution. I'll get to what that is in a little bit specifically, but probably for now, it's suffice to say that this is an important piece of how the advertising industry measures how they achieve what they do. But next slide. This is what I'd prefer to talk about. So that's what we're going to do for the next few minutes. More specifically, next slide, this. There's probably a number of you who are familiar with this system now, having been here a couple of days. So I'm going to talk about an issue that's very pressing for people who operate these networks. And next slide, please. So those of you who've used one of these systems know that a lot of these use a system of identifiers that they use to manage a number of different aspects of the way that you interact with the system. Primarily, these take the form of a card. I think I have one of those in my pocket right now. Look at that. That's actually the one in the photo. And you tap the card to enter the system, then you tap the card when you exit. And in a lot of cases, the distance that you travel in the system determines how much you pay for the things. But I'm not here to solve the privacy problems with that. I'll leave that as an exercise for the people in the room as to how to build a system that will preserve information about your trips specifically and allow you to do a distance-based fare calculation. That's not what I'm talking about. Next slide. What I'm talking about more specifically is the ways in which the transit systems use those identifiers to track for the purposes of capacity planning and other uses. They want to know how many stations to build, how many trains to run on a particular line, and other things like that. And I think I can see Philip's finally tweaked to exactly what I'm going to be talking about now. There are some exceptions to that. Cash payment systems, entry-only tracking tend not to work very well with this, but then the New York system that's pictured in the slide there has a fixed fee. You only swipe in when you enter the system, so they can only really track when you enter the system. So there's limited information in those cases. What I'm talking about are those systems that track when you enter and when you leave. The way that these work typically nowadays, as I understand it, is that each one of those cards contains an identifier for you, and that identifier is logged by the system when you enter and logged again when you exit. And all of those are collected into a giant log, and you can make some queries of those logs to determine, is this the busy hour? How many people are traveling between Shinjuku and Tokyo Station, all of those sorts of questions that are kind of essential for doing capacity and performance planning. You can also do things like look at how long it takes people to take journeys when you have interchanges between different lines and those sorts of things. So really useful for capacity planning. But next slide. Logs are terrible. They create a record of the movements of people through the system and can be used for purposes other than the ones that I described, which are potentially useful. They also provide you with means of identifying when people, say, for instance, are visiting someone that they maybe shouldn't be, or that they would rather other people don't know they are visiting. And so an important thing to note here, though these cards are not tracked, I don't think that anyone knows that this particular number is attached to me. I got it from a machine that I may have used a credit card on, which is a problem. But I may have paid for this with cash at a machine. And so then there's nothing that necessarily ties the specific pseudo-identifier to me. There is still a privacy problem inherent in the system because those pseudonymous identifiers can still be used with various de-anonymization techniques to identify who you are, given a long history of records of the journeys that you take. Next. So what we want to do is collect aggregated information about journeys so that we can protect the information that individual people want. We don't necessarily care about those individual journeys. We just want to know how things are working just in the aggregate. And that is harder than you think. So a design for that. So one simple design that I think has been used in a number of places is you essentially hand a token to people when they enter the system. They carry those tokens through the system, and at the other end, they deposit that token into a bucket at the other end. You encourage them to do so by very good anticipation, but we're almost there. That you encourage them to use the deposit system by potentially making the fare lower for them depositing the thing in the system at the other end. There's a number of different mechanisms that you need to sort of layer on top of these ones in order to make sure that the system works as you expected. In one set of designs, the tokens are anonymous, and we use, potentially you could use something like a blinded token, much like we do in Privacy Pass. Or maybe you can just use a very low entropy identifier that would allow you to sort of identify in the aggregate who people are, but because you have to assign the same identifier to multiple people, you would have some sort of anonymity property that comes out of that because you have to share those identifiers between multiple people. There's obviously a whole bunch of problems that come from this with fraud and various other things because that token is not then bound to anything. People can exchange them within the system and game the system in various ways. So there's ways in which you might need to slap some extra authentication on top of it so that you can trust that the information you're getting out of the system is somewhat reliable. And you can't open that box that people deposit their tokens in at the other end. Otherwise, you can just sort of, you can't get the information out immediately. As soon as someone deposits the information, you have to wait or mix them around a little bit at the other end. Otherwise, you can sort of use the timing at which the token was dropped in the bucket to link it to the person that dropped it in the bucket and sort of learn where they came from as a result of reading that off again. So there we talk about having things like random delays before you open the bucket. You have a bucket and you shake it up and wait for an hour, and then after the hour expires, you can look in the bucket and then, well, it's got the last hour's worth of people in there. You don't know which one of those people specifically deposited the token. Of course, we can potentially use an aggregation system to make those delays a little shorter and mix things in a little more efficiently. And we'll get to that because that's the interesting part. So nice things about these designs are that the tokens are ephemeral. You sort of give a token to someone and that token really only exists for the duration of the journey and the thing that you're interested in measuring. And because the users carry the tokens and can sort of see what the tokens are, they sort of understand at some level, potentially, what it is that they're carrying for you and have some sort of say in how that information is carried. And that you can imagine that this being sort of a consensual process in the sense that in order to access a lower fare, people will be carrying this information for you, and there's a trade of information there, that a trade of information for value, essentially. And the token is limited in terms of what it holds. You could imagine that the token could contain a photo of the person as they entered the stalls in one station, and they carry that to the other station, and then there's a track record that's bound to the identity of this person based on a photo or something like that. But because the user carries it, they can sort of maybe know, depending on the properties of the token, what is being carried around, and so they have some sort of control over that. But of course, the flip side of that is because the user knows what information they're carrying and has to agree to carrying this information ahead of time, the system tends to be a little inflexible in how it's put together. And of course, as I mentioned, aggregation's great, but and it can sort of mitigate some of the problems that we have with things like delays and questions about the size of the anonymity set that you'd get with a limited entropy identifier. Next. So now we go from trains to advertising. This is the interesting part. So next slide, please. So in attribution, you're taking information from one context and you're linking it via a person to information in another context, much the same here. And the basic premise behind attribution is we want to understand how our advertisements are working. And we show advertisements in a variety of different contexts, and all of those are shown with the purpose of having some person see the advertisements and act differently in some other context. And we want to be able to understand, when we show the advertisement over here, the person taking the action over here, whether or not this was linked to, or maybe not consequence. We can talk about causality and correlation here, but whether this was the same person that saw the ad in these other contexts. And being able to measure this information gives you some ability to understand whether your advertising is working. And so when you have attribution, it sort of underpins everything that the advertising industry does in terms of how they understand how to place ads, where to place them, how much money to spend, how long to run a campaign for, what sort of things to show to people, whether it be bright flashing pictures or subtle text or whatever it is that they're trying to accomplish. And we have a problem in that we're taking information from one context into another one, and that creates the ability to link activity for the person. And so we would like to do that more privately. Next, please. So if we have trains on the left, quite simple. You enter the system, you exit the system. These things happen only once. You won't be entering the train system more than once. You won't be leaving more than once for every entering. That's not true of advertising. People will see lots and lots of ads. They'll click on some of them. Sometimes they will be a person who the advertisers think might be a good candidate for showing an ad, and they'll decide not to show them an ad so they can do a randomized controlled trial and say, we've got this cohort of people that we'd like to show ads to. These ones saw the ads, these ones didn't. Has the ad had any effect on their behavior subsequently? And of course, when you exit, people do buy things multiple times. The things that advertisers want to achieve from showing advertising isn't as simple always as showing an ad. It might be that, purchasing a product. It might be visiting a site. It might be signing up for a newsletter. It might be that you're looking to see how far through your online shopping process that someone has gone through. And probably the thing that underpins all of this is that when we talk about trains, the only real context that matters is time of day and some other relatively minor things, whereas with advertising, context is everything. If you're an advertiser and you're placing ads on a newspaper, and the newspaper has an article on, let's just say, one of the classic examples here, they have an article on a plane disaster, and you're an airline and you showed an ad there, you might find that the performance of that ad differs to the performance of an ad shown against a travel food blog thing or an article about travel in some other country. And so context is everything for advertising, and they will really care about pulling a lot of that information in. Next. So interoperable private attribution has a similar design in some ways to the ones that I talked about previously. More similar, in fact, to the tracking system that I talked about before with the advertisers for unique identifiers for everyone, but it uses a different approach. So the idea is that in the different contexts, people will conduct various pieces of activity, whether it be viewing ads or buying stuff or visiting websites, whatever advertisers care about. And everyone has essentially an identifier. Now, how they get that identifier is gone in. We go into a whole lot of detail in the document. But the thing is, that identifier is a secret for that person. No one other than that person knows what that identifier is. And most of the system exists, and all the complexity in the system exists to protect that information from ever being made available to anyone outside of the person who the identifier is assigned to. When a website shows you an ad or you purchase something, the website can request an encrypted copy of the identifier. And in fact, I should have said encrypted and secret shared copy of the identifier. The sites then gather that information into their logs just as they would any other identifier, except for the fact that now we have two different sites that have encrypted blobs that do not correlate in any way. There's no way for those sites to look at that encrypted blob and say, this is the same person as this. So in effect, those logs are useless to them for the purposes of linking activity across sites without some extra help. Next slide. So what the sites do is they sort of collaborate with each other and collect all of the logs that they have across multiple different contexts, and they put them into a huge pile, and they add some information that's relevant to the system, and they submit to an MPC, and that MPC will perform a computation and give them the information in an aggregated form on the question that they want answered, which might be how many people saw this ad and then bought the shoes, or how many people clicked on an ad and bought any product on this website. The shapes of the queries are largely under the control of the sites in question. The MPC performs a computation to match items in the log up to the same person and perform an attribution algorithm, the details of which I won't go into here because it's boring. The net result of this, yeah, Philip says, yes, boring. Chris is laughing. The output of the system is an aggregated result, which sort of says, which is broken down effectively into a histogram. For this campaign, potentially you have this many. For this campaign, you have this many. For this campaign, you have this many. And one of the nice things with this is that the MPC can perform this computation without anyone seeing the underlying identifiers, which is critical for privacy purposes, but it also performs a computation without the MPC even learning what the query was in the first place. So one of the sort of primary concerns that a lot of advertisers have is that they have business sensitive information that they're submitting as part of these queries, and they don't want anyone to be able to get access to that information who might be a competitor to them and be able to use it for their own purposes, which is also an advantage. Next, please. I am getting through these. So in IPA, this is all I'm going to talk about MPC. We use a multi-party computation. The great thing with MPC is you can perform any computation without seeing what the inputs were. Any computation can be performed if you can add things and multiply them. Just like in logic circuits, if you can OR and AND, you can basically do anything. Or is it OR and NAND? I forget exactly what it is, but it doesn't matter. The thing is, all you need is time, network capacity, and a ton of CPU, and you can perform any computation at all. The trick is reducing the amount of money that you spend on the computation, and there's a lot of tricks. We found that the best trick so far that we've found is a three-party honest majority MPC. That is, there are three entities, and you trust that two of them will faithfully execute the protocol and not collaborate to share values with anyone else. And we can provide information theoretic security guarantees that don't require any sort of complex assumptions on the cryptographic side of things. And we can perform a whole lot of basically generic MPC. We do some sorting. We do some comparison across different lines, and we can produce an output from that. The details are linked later on in the talk. Next, please. So probably our key privacy hook here is that we're looking to use differential privacy for this to hide the contributions of individuals to the system. Obviously, we're revealing an aggregate result at the other end. Someone is going to learn something about the inputs that were provided, but we can use differential privacy to ensure that the information about individuals is statistically covered by noise in the output. In order to do that effectively, we need to find ways in which we can understand the limits of how much someone can contribute to the system. And we have a number of mechanisms in place to do that. The first one of which is that we're not restricting the amount of information that sites learn over time. We're restricting the rate at which they learn information. And so there is a budget that sites are given, which is you get this much every week, and that renews at the end of each period. That's not great. Given infinite time, infinite information will be released, but the alternative is to progressively degrade the usefulness of the system over time as we release information. You can imagine if you use the system for 5 weeks and then the site uses up the budget, they learn nothing more about that person forevermore. Doesn't sound like a really great solution. We're going to have to look at other ways to ensure that individuals are not targeted. We have not yet decided what the key tuning parameters are. And so the shape of the noise, how much noise, and how much error resilience we need to have is very much an open question right now. We're doing some studies to work out exactly what those values might need to be from a utility perspective. And there's going to be a lot of debate about what it means to protect information with an epsilon value of, say, 0.1, as opposed to an epsilon value of, say, 400, which was the joke that was running around the other day. Let's just say that 400 doesn't look like very much noise. Next, please. Right. So in order to facilitate that sort of thing, we need to make sure that when an encrypted identifier is provided, we can sort of trace it back and bound the scope in which it is used. And so encrypted identifiers will be bound to the site that requests them. They will be bound to when they were requested so that they can't be used in another time period. And we're also binding other information such as the type of event. And the type of event is sort of critical here because there are two sorts of queries that we're asking. In sort of generic unbounded attribution, you might show ads on multiple sites and be wanting to track outcomes on a whole different set of sites. But we've set a restriction on this one to say that when you make a query, you have to choose one site from which to deduct budget. And that site is on one side of the query, and then you can have multiple sites on the other side of the query for which the budget does not matter. And so we have to know which site is involved and which sort of query will be involved for that particular event, so that we can then cap the number of that type of query for that website in that week. A little bit funny like that sometimes. We also have capping within the MPC system, which is second to sorting the most expensive part, because you have to go through every single record and effectively compare it to every single other record, which is massively expensive. And that's a research problem, I think. And then there's all sorts of other commitments, like the sites need to commit to using a specific MPC system. They can't just take their events and ship them around to different MPC systems. Otherwise, they would be able to get more access to more budget over time. And there's a whole bunch of other things that we probably don't need to go into. Next slide, please. So why did we go through all this trouble when we have the simple token-based thing? I think primarily from, this is from a utility perspective. IPA offers advertisers a lot more flexibility in terms of how they process that information, with a hard backstop on this, with the differential privacy and all the security measures that we use in MPC to ensure that the identifiers don't leak out. The ability to use their existing logging system with a different sort of thing that substitutes for an identifier means that they can operate existing fraud prevention mechanisms without having to integrate fraud prevention into the system. I mentioned in passing for the token-based one, there's a need to sort of carry tokens through the system to prevent people from fraudulently misrepresenting the fact that there's ads were shown, for instance. Whereas in this case, it relies much more on existing systems than otherwise. Of course, it may still be the case that we want to integrate more tightly with those fraud prevention mechanisms, but the idea is that we would not over-index on that one, and it wouldn't be critical to the design to have that integration. On the downside, however, the flexibility that we're offering here does sort of hurt some of the accountability properties that we're looking to obtain from a system like this. One of the key concerns that people have raised with a lot of these systems is that they are inscrutable. The information about queries is opaque to everyone involved in the system, even if, in this case, even if the MPC system published the details of every single query that was ever made through it, we wouldn't really know what those queries entailed, because they just contain a whole bunch of random goop that has been secret shared, and we don't know what to do with that. So we do have some challenges in terms of making the system understandable and in particular auditable from the perspective of users. And of course, MPC performance remains a challenge. We have, I think, some reasonably good stories about communication efficiency and whatnot with our current implementation, but the numbers that we've received from some of the larger actors in the advertising industry are scary. We're talking about running a trial now with millions of records. The number 200 billion has been raised, and it turns out that's a very large number to handle. And I think Philip will talk a little bit about some of the things that Google have been working on in this area to sort of help us scale these sorts of systems out. But this remains a big challenge, particularly when we talk about maintaining the privacy guarantees that we're looking for. Next, please. I'm making progress here. Okay, so the reason I'm here is to sort of make people aware of this. The reason I'm not in the IETF is the first point here. This is still largely active research. There's ongoing discussions with the advertising industry. There's some really good engagement at the W3C. We I think, have established that this is potentially quite feasible to do on at least a small scale, the scalability questions notwithstanding. We're working out the details of the algorithms. We continue to take 5% off the communication costs several times a week. So things are moving pretty rapidly on that front still. Very unstable, I would say. We're looking to run trials this year with real advertising using the identifiers that certain actors in the ecosystem have made available to us and not removed. Thank you, Google. We'll see how those trials work out. We're essentially synthesizing the operation of the system without any involvement from browsers and user agents. So that will be interesting as well. What we're hoping to do ultimately in the future is work out which one of these proposals in the space is most interesting, and we will go from the W3C when we're talking about this and look to make some proposals into places like PPM Working Group and whatnot, where we can talk about real protocols for building these things. We're also looking at broader applicability as well. And next slide, I think, has the only other thing. So that's just an encouragement to join us.
Great, thanks, Martin. Any questions for him? We have roughly 4 minutes. Brian, go ahead.
Hey, Martin. Good afternoon. Awesome talk. I have a question about. It came up in a couple of places. MPC performance is a challenge. Are these challenges primarily the computational challenges? I mean, are we talking about like extremely superlinear performance at the multi-party computation sort of there, or are we looking at the communications complexity? Because I know the last time I looked at all of the basic stuff about 10 years ago, there was still some low and medium hanging fruit in the sort of internode communication. There were a lot of places to squeeze that out. I'm guessing that's been squeezed out. So is this a thing that you can just throw a lot of compute at? Or are there like superlinearities that make that 200 million to 2 billion be you're using a medium-sized cluster somewhere to you're renting all of your favorite cloud provider?
Yeah, so a lot of this is algorithmic. So the algorithms that we're using here are, for the most part, linear, which is fine. The primary challenge, well, Philip will talk about the scaling in terms of being able to scale out once you get superlinear. I think we've got some n log n in our algorithms, which is very bad once you talk about very large numbers. But if assuming that those sorts of designs work out for us, and I think that they're showing a lot of promise, the primary challenge here is actually we're spending a lot of time on communication rather than CPU time. We do hit the AES instructions very, very hard. So it's not like there's no computation cost here. But when we started on this, we were looking at, I think, in the order of, for 1 million records, we're talking about spending about 40 plus gigabytes of communication, which for something on that scale would be bad in terms of being quite expensive just to pay for the bandwidth. I think we improved the sort performance over the time by, I think, 30 to 40 times. And so we're now in the ballpark of like reasonable, and we're continuing to find some more tweaks. But we're still talking sort of multi-gigabytes per million records, which is
but the complexity, the complexity that needs to be squeezed out is still that communications complexity as opposed to what's going on each node.
Yeah, very much so.
Okay, cool.
Yeah.
Thank you very much.
Yeah, Martin, I have 2 questions. And they're both kind of meta, so bear with me. So the first of which is the two of the hard problems that this particular work seemed to set out to solve was one, sort of trying to define like what was like the MPC functionality you needed to solve the problem that like the ad tech people needed. or claim to need in a particular case. And then the second one, which is what you're all turning on right now, is now that I have this particular functionality defined, how do I implement it in a way that's like performant and we can deploy it and whatever?
Yeah.
I'm wondering if you could speak to how you went about perhaps like defining the functionality and refining it down to what you have now. Like there's this concept of cross-device attribution that's being discussed in the chat. You can't see it, but there's like a lot of it's not the simplest thing in the world, but it seems like it was the result of a lot of iteration, a lot of discussion with the stakeholders. And I'm wondering if you can say anything about the process by which you converged on this particular type of functionality and why you think it like effectively solves the problem.
Boy, do you have another half an hour? This is very much the process of iteration on these things. I think there was a lot of people who looked at this problem very, very long and hard and tried to reduce it down to something very, very simple. So those familiar with Apple's private click measurement will sort of recognize a very, very simple design that doesn't achieve very much from a utility perspective, but sort of very, very much clarifies the sort of shape of the thing that we're trying to do, which is we're taking information from here and we're passing it across to here. And there's a single person that represent the connection between those things. And we want to keep their involvement in that private. For the most part, however, this is really about understanding how the advertising industry uses that information. And there have been many, many hours wasted on going through, I won't say wasted, spent on going through the finer details of how measurement is an integral part of the advertising business. And that has happened over the course of probably 3 or 4 years. The W3C Web Advertising Business Group has talked about this at length and produced some fairly coherent documentation on what it is that they do, as opposed to what it is that they need. And then I think various actors in the space have sort of made their own determinations of what it is that the sort of need versus want judgments and sort of come to different conclusions. And so there continues to be debate about certain things. And you mentioned offhand the idea of doing cross-device attribution. So can I take an ad that I saw on my phone across to convert on a PC somewhere else and be able to link those two events and have them come out through the attribution system as a positive result? That's something that continues to be under debate because of all of the really interesting privacy implications of being able to do that. When you can do that, is it possible then to connect to what you did when you physically entered a store and bought something with cash? That would be, I think, for some people a little surprising. And so we're going through a bunch of debates about where the line sits there. And some of this, I think, it's not a Boolean question of needs and wants. There's a continuum, and you'll find that there are people at different points on that continuum for whom the question at that point is existential. And so some of these things can get a little heated. Yeah.
Yeah, great, thanks. So just, I won't ask the second question because there's not time. I just wanted to perhaps add some context to the reason I asked it. So there's a lot of like really brilliant people who like work in MPC and they spend a lot of time like implementing really efficient protocols for doing things or implementing a functionality that turns out maybe not to be the right functionality in practice. And all the work that you all spent hours like refining this problem to sort of basically, say this is the functionality we actually need.
Yeah.
Really smart people go out and like tell us how to implement this in a way that's performant. I wonder if like, this sort of meet in the middle approach is a useful way to kind of go about applying the way you went about building IPA and designing it for other types of use cases that might use MPC in the future.
Yeah, it's an interesting question. I don't know what the answer is. There's always this should we build this question that underlies all of these things.
Sure. Yeah. All right. Thank you.
Hey, Martin, thanks. My question was, so we seem to need like 3 servers at the back end to actually do the MPC.
Yeah.
Just wondering, I guess it wasn't clear to me, would those be the advertisers or would it be just independent
Oh,
parties?
right. Yep.
And would they, like, who are you imagining that they would be? And would they be just the 3 in the whole world, or would there be different clusters?
Yeah, I didn't go into that much detail. The proposal talks about this at some length. The idea is that you have to trust these guys not to work with each other to undermine privacy. If your MPC system is willing to share their information that they get with other nodes in the MPC system, you've basically lost all of the privacy protections. So from my perspective as someone who works on a browser, I would want to know that I can trust the 3 helper parties, we call it, in the MPC system, not to do that. But that's all I need to trust them to do. And so we've gone from being able to sort of do this computation with a great deal of trust in whoever does it, which is a practice that happens right now in the advertising industry quite a bit. They call it, they often refer to clean rooms, which is where some trusted entity is given access to all the information, and they go off into a little room. Maybe it's a skiff or something like that, and they can do the computation and they come out with the answer. But you have to trust that they're not going to leak that information, essentially. Here we have a much lower trust. And we've spent a lot of time working on who those entities would be. They would not be the advertisers. They'd probably not be the browsers. They would be sort of a neutral party. And there would be more than one option. The idea is that an advertiser would be paying for access to the MPC service. And so we want to have some sort of competition there to sort of incentivize efficient delivery of service to keep the costs down. And so there would be multiple there.
Thanks. Jonathan? I'll be locking the queue now, I think.
Yeah.
Jonathan Hoyland, Cloudflare. If you're having it run by a third party that's just winning an auction, say, does that third party have an incentive to say, or can they say, oh, I'm definitely running MPC, and then actually in the background they have their nodes clued, compute the answer really cheaply, and then return you the correct answer. And they're not doing it to break privacy. They're doing it to save money because, like, running MPC is expensive.
So we can talk about TEEs if you want, which is essentially the story that others have chosen to adopt. The idea is that there would need to be some sort of oversight for these entities to sort of verify that they are indeed conducting things, much in the same way that the model that we imagine using here is much like the CA browser forum, where there's a collection of browsers or user agents in this case that would get together, set a set of rules that we would expect these MPC systems to abide by, and there would probably be some sort of auditing process that would verify that that is indeed what they're doing in practice.
Could we do something stupid or well, semi-stupid, where we just say part of the response they have to give is, I don't know, the last step of the MPC computation, or like some like proof that they actually did the work? It doesn't mean they didn't break privacy, but it means that they don't have a financial incentive to skip the steps.
Yeah, so last week we spoke with some MPC researchers at Boston University who immediately asked, so have you talked about using verifiable MPC, which is a thing?
Okay.
Far more sophisticated than what you described. Also not ready, was their assessment. It's probably going to tank performance, and the research on that is limited, to say the best about it, as far as I understand. So things are possible, but we're not at that point yet. I think we're more likely to want to rely on the sort of trust and verify systems that we use currently, as much as we might aspire to something better. That's the best that we can manage right now.
Thank you.
Thanks, Martin. Thanks also for, we went to like pretty over, so thanks for answering all those questions.
Right, yeah, next up we have Philip to talk about secure partitioning protocols. Just let us know how you want to advance. We can do it for you.
Or if you want to, I think
I have too many animations and stuff.
Oh, okay, all right, then you should do it.
Thanks. All right, yeah. Thanks, Martin, for this great talk and great images in the slides. I don't have as many of those, but yeah. So I'm going to try to go a little bit more into details about how do we scale this, or how do we scale any such aggregate system, such that it actually runs on real machines that we have. Because we heard these sizes of these logs, or the sizes of the data, is usually quite large. So if you think all of the impressions that we have across the web are now supposed to be running in this one single MPC cluster, that's going to be billions of impressions from billions of clients, and it's a lot of data. So just a recap, so the way we envision it in the abstract sense is that all the clients submit all the reports to the single MPC cluster. That MPC cluster performs its MPC, and we get out the aggregate report that is anonymous or differentially private in some way. So what we crucially need here is to have, or to put it into train speak, that the tokens of a particular user end up in the same machine, right? So if we distribute this now, so if we want to have multiple clusters that run on, that distribute all the users across them, then we need to make sure that all the clients or all the reports that belong to a particular client end up in the same cluster. Now, if we just reveal, well, this is me, I want to be, this report belongs to me, and we have some pseudo identifier, then we're back to square one. So that doesn't solve the problem. That just has another identifier that we do not want in the first place. So the goal here is to have a secure sharding protocol or a secure partitioning protocol that allows us to do this partitioning of encrypted reports without actually revealing a clear text identifier, or at least without revealing it without some additional privacy measures. So just a high-level view of the goal. So as I said, inputs from the same client should end up in the same shard. That way we can ensure that the downstream MPC works, so the IPA protocol, or whatever aggregation we want to run. We want low overhead, so the MPC is expensive as it is. We don't want to blow that up by 10x just to do efficient partitioning. And we don't want to affect the correctness. So ideally, we want to have a result that is equivalent or equal to what we would get if we had this big machines that run the MPC. The assumption that I'm making for the protocols that I'm presenting here is that we have some bound on the number of contributions from honest clients. In practice, you can probably think of a very large bound. Ideally, you want to have it somewhat lower because that's going to affect the overhead of the protocols. And again, the second assumption is, but I think that all of these systems will share that, is that we have many, many clients and quite a few shards. So thousands of shards, but maybe not billions or millions. All right, so the blueprint that I'm presenting here, and I'm going to switch to a two-server model now, simply because the protocols that I'm presenting here, they work quite well with two servers already. Even if the larger MPC system has 3 servers, one of them could be idle for that, or you could distribute one of them across 2 of them, doesn't really matter, but conceptually 2 servers here works just fine. So we have a client who has an index or an identifier and has a value or a payload. And what the payload is for this presentation, we do not care. It's something that's secret shared, that's encrypted, that will be used by the MPC system. We just have to pass it through correctly so that in the right position, we have the right payload for the same client. And then we have 2 servers. One of them has an OPRF key. So a PRF is a pseudo-random function that basically maps the client identifier to some random space. And the key for that mapping is owned by one of the servers. And to get a bit ahead, the second server will learn the result. So the first server knows the key, the second server will learn the result of this OPRF computation, and that will allow it to do the partitioning or the sharding. In order for that to be private, we need the first server to also add some dummy contributions. So there will be some overhead here by just adding some dummies, but these dummies will ensure that whatever the second server then learns is differentially private again. So basically, it achieves the privacy goal that we want for the overall system. So yeah, as I said, the second server will then map the output of this OPRF to the partitioning to the partition that then gets sent all the encrypted values to. So I'm going to present two protocols that achieve that, or two approaches. And their main difference conceptually is in how does this OPRF look like. So the first of them, that I call dense partitioning, is where the OPRF output value is directly the space of shards. So if you think we have 1024 shards, that is a 10-bit domain. That means we have a 10-bit output from the OPRF, and we can directly use that as the shard ID. So what this protocol does is it maps indexes or client identifiers to a shard ID directly. That is nice. So if we can have such a protocol, that's already solving the problem directly. And so again, so the way it would work, the client encrypts both its index and its value. The server adds dummies, in this case, to every possible output value, so to every possible of these 1024 values. And then that gets sent to server 2. And now server 2 decrypts, gets the OPRF value, and directly can assign every single contribution to a shard because it's in the output that it got. So if we only have a couple of shards, then this actually is quite performant because the overhead that we add, so the number of dummies that the first server has to add to each of those shards is roughly 50 times what the maximum contribution of a user is. So that means we add 50 dummy users basically per bucket. And now if we think back to the assumptions we made, we had billions of users and thousands of shards. That means we end up with at most 50,000 dummy users out of billions. That's not much overhead, right? So this is very cheap. And the privacy parameters I put here, epsilon 0.5 and delta 10 to the minus 11, that's pretty conservative. So that's pretty private, but we could make it even more private if we're willing to pay with the bandwidth. So that's nice already. And I believe that for the IPA protocol, for example, that would already be sufficient. So that might be a protocol that maybe has some caveats that I'm going to go into in the end, but overall, conceptually, it solves the problem of partitioning this computation. But sometimes what we would like to do as well is to do some local aggregation too before we start the MPC. And here is, so one example, for example, is that instead of directly passing in the values into the MPC and doing some complicated computation on it, we might want to aggregate per client first. So if the values, for example, are conversion values, how much did a client spend? Maybe we want to add that up before we do the MPC, and that just saves us saves us runtime inside the MPC. So that might make things more efficient here. But the trade-off now is that if our OPRF value maps client IDs directly to shard IDs, and we don't get some kind of pseudo client identifier, then we cannot do a per client aggregation anymore. So what the sparse partitioning protocol that I'm presenting tries to do is to solve this issue. So it allows us to get an identifier that is not just as small as the shard IDs anymore, but it's a long ID that actually is a pseudo client identifier. Now, you might ask, how is this then private, right? Don't we now create another ID for the client and we're back to square one? Well, here the main idea is that by adding dummy contributions, again, as in the previous protocol, we can inject dummy clients in a way. And that ensures that whatever the server sees as its components, so as its pseudo index and encrypted value pairs, it cannot be sure whether that's a real client or whether that was some dummy injected by server one. And we have the non-collusion assumption here as well as in the IPA protocol. So as long as one of the servers is honest and is not, and the two servers are not colluding, then we're fine. So the overall structure of that protocol is similar. So again, the client encrypts under some semi-homomorphic encryption scheme their index and their value. The first server obliviously adds dummy contributions and performs the OPRF computation, and that gets sent to the second server. And that second server now maps the OPRF value, so can map that actually arbitrary to shard IDs, and then can do local aggregation per client. these are like, this is a more detailed version of the same slide as the previous one. Here, I basically just expanded the value. So if you think of the three-party setting of IPA, we have 3 secret shares that are separately encrypted, but otherwise feel free to ignore the slide. Regarding the overhead that this protocol brings, it's going to be slightly heavier than in the dense partitioning. And the reason here is not due to the partitioning. So if we want to assign in the clients to buckets or to shards, the server has the pseudo identifier in the clear, right? So it can just arbitrarily map them however it wants. And if we only add a slight overhead over the minimum that we need, so this is this M prime here, which is about the maximum contribution that a single client can have. So then we're actually having an overhead that's, we're having a blow up that's less than in the dense partitioning protocol. However, the number of dummies that the first server adds, that's going to be much more than it was in the dense partitioning. And intuitively, you can think here that we have a much larger OPRF output space. And in order to mask not only the contributions of clients that appear, or the contributions of clients that have many contributions, but also the ones of clients that only have a very few contributions, but there might be many, many of these clients. Those are the 2 edge cases that we will both have to protect against. And the overhead, again, for the same example parameters here is like 10%. So that's a lot more than we had in the dense partitioning. It's still not 10x, but yeah. So yeah, here just a very high level view on how we can make this sparse OPRF computation private at all, because that's somewhat unintuitive, right? We get a pseudo identifier where we are sure that every client has its own identifier, but at the same time, we don't learn anything about individual clients. And the magic here is to basically view these, this collective output of this OPRF computation as a histogram. So what the second server sees is this kind of multiplicity histogram. It knows I have this value and it appears 10 times. I have this value, it appears 100 times. But I don't know which value maps to which client. And all we have to protect now is this multiplicities. So we have to make sure that the fact that 100 appears in this list that the server gets does not reveal anything about a particular person. And we do that by basically adding 2 kinds of dummies. So one is supposed to hide the contributions that are common, so clients that contribute many, many reports. And the other is to contribute, to protect contributions that are rare. So clients that only have a couple of reports or only one. Yeah, the details are, the details are basically we choose a threshold, and below the threshold, we do the same thing as in the dense partitioning. So for every possible value below the threshold, we add a certain amount of dummies. And then above the threshold, we do something slightly smarter, where we take existing ciphertexts, we duplicate the underlying client identifier, and we replace the value by a 0. And that way, it doesn't affect the output of the computation, but it hides the clients that have many contributions. All right, so in conclusion, these distributed OPRF computations, in practice, they are quite performant. So in the paper that I link here, we actually have some performance numbers. The overhead is manageable, I would say. So for the dense partitioning, I think it's already there. It's basically non-existent, the overhead, apart at least from a communication perspective. So computation, you still have to do some, of course. For a slightly larger overhead, we get this nice additional property that we can do local aggregation. And yeah, it's up to discussion whether IPA actually needs that or whether we just can go with the dense protocol and be done with it. So why am I presenting this here? So first of all, I would like to know a little bit what's the interest in this research group or anywhere in the IETF of standardizing protocols like this separately from things like IPA. So IPA is currently being discussed in the W3C, and yeah, most of the concrete discussions happen there. But IPA is not the only protocol that we're going to see in this space. I think it's going to be like not only ad attributions are being done currently with third-party cookies, but many, many other things that also might benefit from this concept of not aggregating, not collecting individual data and then aggregating, but aggregating directly in a protocol. And I think these as well will have to have some kind of scaling mechanism and some way of partitioning their inputs. And I think if we can come up with a standardized way of doing that, then that might help downstream to make other privacy preserving aggregation functions more easier to develop and easier to deploy. So the second point here is what other protocols might this be useful for? And I also discussed this topic in the PPM working group. So currently there is this DApp standard that's being developed, and that has a nice property that you only touch every user in separation. So you don't do any computation across users like in IPA or across contributions. The only thing you do is aggregate, and that you can trivially shard. So this is not needed for DApp or VDAF style protocols, but it might be needed for others. For example, I don't know what this safe counting standard is about, so would like to know whether this might need something about for partitioning or not. And then finally, do we need additional properties? So is the two variants that I presented here, are these enough? Do we maybe need some kind of stable sorting of inputs? This is also something that's being discussed in the context of IPA. So yeah, these are the questions I like to bring to the room, and thank you.
Thanks, Philip. Chris?
Thanks, Philip. Chris Patton and Cloudflare, I guess. Yes, supposed to say your affiliation. I think this is definitely interesting. I don't know if it's interesting as like an independent thing. It might make sense to say like take some NPC that we're working on and apply it to that draft. Would be my suggestion. I don't know if it makes sense as like a draft that says this is a paradigm that you could apply to different NPC things.
So you basically saying whenever we develop a protocol, we should add something like that into that particular draft for that protocol, but we shouldn't separate it out.
Yeah. As like a first step, like take the IPA code and see if you can shard it and see if you can improve, like get it to scale better. I don't know. Oh.
Yeah, I didn't do this. Chris, you go first. You're on the queue. But you're in the queue?
Other Chris.
Sorry, Chris Patton was on the queue. He just Martin.
Oh, he just needs to get off. All right, I'm going to put myself on queue. Martin Thompson, it seems like the sort of bounds you're talking about are sort of fundamental rather than anything else. Is there, how confident are you that these sort of numbers are just what you end up having to pay based on your analysis, or is there potentially some other approach that would produce different overheads?
So these numbers are just for whatever I presented here. So there might be other approaches that are much cheaper or much more expensive or have a different trade-off between computation and communication and so on. So yeah. Okay. This is in no way like a theoretical lower bound or anything.
Okay. Yeah, that's really what I wanted. Thanks. The other thing was, I'm not sure that in IPA we're as confident in our ability to cap the contributions from individuals as this would require. That's something that I think we probably need a whole lot more discussion about in these contexts, but the ability to deal with sort of Sybil attacks and other things like that really do concern me a little bit, because it's great having these theoretical results that sort of say that we can do this sharding under the following assumptions, but when one of those assumptions doesn't hold, from a practical perspective, it's very, very hard to reason about, and we've been back and forth on this one a lot.
I think we should dig into that, because I mean, you're right in the sense that in IPA, basically any malicious advertiser or website whatsoever can create as many reports as it wants, right? So you don't have this guarantee that there's a limit on the number of reports. But I think you can make sure that in the downstream MPC, so you can still sort it in a way that once the second party sees all these reports, it will know whether they're over the limit or not, right?
Yeah. So,
and then inside the MPC, you can start filtering and counting and saying, well, is this more or less? But yeah, that's probably something that's
It needs some
specific
work.
to
Yeah.
IPA.
Yeah.
Yeah.
Thanks.
Thank you for the presentation.
Yep, thank you.
All right, Wouter, you're up next.
Cool.
Would you like us to share your slides?
No, if you can, I can do that myself. Right, 1 second. How do I do that? Sorry about that, people. How do I? Where's this button? Sorry about that. Ah, there we go.
Perfect.
There we go.
Nice.
Cool. Everybody sees this. Everybody hears me.
Yep, take it away.
Okay, so my name is Ote Lux. I'm currently a faculty member at CISPA, and I have been working quite a lot on DPTT. If you forgot what DPTT was, right? DPTT was one of these massive academic-ish initiatives to design privacy-preserving proximity tracing. So just to give you an idea, right, this was with tens of academics where we proposed something in early March. This was then adopted by Google and Apple sometime in April, and the first apps that were using the Google and Apple version of what we initially proposed were rolled out in June, right? So this is a timeline that is relatively tight. And then what I will not be talking about today, we kept on working with this, especially in the Swiss context, because I was at EPFL at the time, to keep developing these apps and to potentially add new features or think about new features and the consequences of this. And in this talk today, I just want to give you a little bit of a few of the things that we learned from this, and then particular with a kind of technical angle to this. So if you think about us being academics, right, or at least me being an academic, right, this was a little bit different than what we would normally do, right? These were really in a setting where you have millions of users, potentially tens of millions of users, and a huge time pressure to design and deploy this, right? We did this within weeks and months, right? If you remember the timeline on the previous slide, we kind of got the first prototypes within 6 weeks, including the design, which is not something that you necessarily do. And right, this also necessitated keeping things very simple so that we could easily verify this and kind of avoid all the fancy new stuff, including, for example, MPC, right? I don't think it ever came up in this particular context, right? But it was not something that we could really afford to do in that setting. And because we wanted to deploy contact tracing in a digital form so quickly, we had to use existing infrastructure and hardware. And I couldn't make this blink on my PDF, right? And also kind of don't want to, but this existing infrastructure and hardware will be sort of a theme in the rest of this talk, because doing that really had a lot of consequences about what we could do and could not do. So just so that we're all on the same page, right? What do I mean when I'm talking about digital contact tracing? I mean kind of the obvious thing, right? Like, we want a system that after somebody has tested positive and has been in contact with some other people for long enough, then these other people that have now been potentially exposed to the COVID virus get a notification so that they can take appropriate precautions. Now, that is all that essentially most of these systems do. There could be other purposes of this system that I will not be talking about, right? But in sort of essence, what we try to do while designing these systems and reasoning about these systems, we try to build these systems with purpose limitation in mind. So we wanted these systems to be only used for notifications and build them in such a way that you cannot use them for any other purposes. And now you might be like, why are you telling me this, right? Now, if you think about digital contact tracing systems and what they would need in order to function, you will immediately realize that there are quite a lot of risks associated with this type of system, right? Because in order to do this notification to quarantine somebody or to send somebody to get tested or whatnot, when they have been in close enough and long enough contact with somebody that will test positive in 3 days, right? The system must embed a lot of social contact information between people. This information somewhere, somehow needs to be there in order for it to serve its purpose of notification. And this means that depending on how you build this system immediately runs the risk of one, revealing these social interactions between people, right, which we know are very privacy sensitive, revealing potential medical information about people, namely who tested positive or who potentially was exposed to COVID. Like maybe nowadays this is not so sensitive anymore, right? At that time when we started doing this, all of this was brutally sensitive. And then depending on how you actually built this, right, this might actually lead to leaking location traces, as well as give the option to do some kind of population control, if you wish, right? Where one might think about this system being used to quarantine certain people and other people not. And we were conjecturing all of these things sort of early 2020 that these might happen, and then design systems that have this purpose limitation by design, right? So you cannot really use them for anything else. But at that time, we didn't have great examples of what could go wrong, really. But nowadays, this is much easier, right? So I took just a couple of things from the news just to give you a little bit of a flavor of all the things that actually did go wrong with the deployment of various apps in this setting, right? So, or with analog versions thereof, right? So we have the German police asking for contact tracing data in their effort to fight crime, because, you know, once you have that data, you might as well use that for something else. We have stories about China potentially using COVID control apps to actually do population control and to limit the freedom of free movement of activists, for example. We have bartenders harassing people. And then we have like ye good old data leaks associated with these systems, but that then ended up leaking particularly sensitive data about these locations in Australia, including defense sites and domestic violence shelters. So really these things that we conjectured initially really came to pass, right? And if you zoom out a little bit, what is behind a lot of this is that whatever you build, the infrastructure that you build really matters for what is that will be used, right? If you build a road, people will drive on it. If you build a contact tracing system with a lot of data in it, people will come and ask for that data or try to use that for different purposes, right? And you'd be surprised kind of by the amount of interesting, shall we say, with deliberate scare quotes, suggestions or questions that we got while building these systems. Like, could we also use this system for X, where X typically was not such a nice thing, right? So which brings me back to the previous point, right? It's really important to design these systems with purpose limitation in mind, so that when you roll out these systems, like especially when you roll them out at this scale, right? And we have talked about other systems again today as well that we're also rolling out at pretty large scales, right? To essentially everybody, right, or a sizable fraction of your population. And I really think that this way of thinking about, okay, what could potentially go wrong with these systems, and how do we ensure that really the only thing that they can be used for is what we initially envisioned, is really important in that setting. Now, let's talk about something a little bit more technical, right? So I'm presuming most of you have heard some kind of version of this story before, but just so that we're all on the same page, right? Let me quickly sketch how the initial DPTT design that was then adopted worldwide, right, after some modifications works. So because we wanted infrastructure that was out there, right, we opted on using phones with Bluetooth low energy beaconing. And this means that if a user would install their contact tracing app, this app would start transmitting random beacons using Bluetooth, and other devices in proximity would receive these beacons and store them in a list of seen beacons. And that is what all these devices do, right? So phone B will receive the beacon from phone A and will store it in this list. But maybe phone C is so far away from A that it doesn't receive it and therefore does not store it. Now, in practice, it will store a little bit more, like signal strength, etc. But this is the rough idea. And then to prevent some tracking as a result of these Bluetooth beacons, apps will typically rotate these beacons, let's say roughly every 10 minutes. Now, this by itself doesn't get you any proximity tracing, right? But you might realize already that this list of scene numbers is kind of like a local proxy, if you wish, right? A decentralized representation of proximity to other people. So we can leverage that to do exposure notification in the following way. So once somebody tests positive and receives some upload authorization from the hospital at the bottom of my slide, they will enter this authorization in their phone, and then the phone will upload the list of beacons that this phone has been transmitting, essentially saying to a central server, here are all the beacons that have been transmitted by this device that corresponds to a positive user. Now, all other phones in the system will download these lists. And then, if you remember the previous slide, right, phones have two lists. Lists of beacons that were marked as transmitted by positive people and a list of beacons that they received. After that, it's just a simple matter of doing a set intersection operation, right? Your phones determine, okay, how many of these things that I received, right, were actually by positive people, and then do some kind of either simple or more complicated exposure notification to determine whether to notify the user or not. Now, there are all kinds of different varieties of this type of decentralized architecture, and a lot of them kind of differ in how they do this upload of this list, right? Because you might imagine that if you're looking at tens of millions of users, you will have a lot of positives, and then in particular, the downstream download costs for individual phones will be very high. So different designs do different compression strategies on how to upload this list, typically generating them from a seed or several seeds rather than uploading them all individually. So this is roughly what we initially designed, right? This got then adopted by Google and Apple as part of their exposure notification framework, with a bunch of tiny tweaks that are mostly around how this cryptography works. Now I want to take you back to what are the consequences of choices on let's say, the hardware and infrastructure layer. So I told you kind of this sort of blue sky kind of story, right? You will just transmit some Bluetooth beacons and all is good, right? But now in practice, transmitting Bluetooth beacons is a little bit harder, right? So we're dealing with phones that have to transmit these Bluetooth low energy beacons. But at the same time, we don't want, or nobody wanted, right, to design an app that would drain your battery in 1 hour flat, right? Because adoption is everything in these systems. And if you would build a system that drains your battery in an hour, nobody will install these apps. And this trickled down in many different ways. First of all, this meant that we could really only use some kind of broadcast primitive rather than a connection primitive, because doing connections is much more battery intensive. Doing broadcast that really limits the amount of payload that you have in doing your broadcast because of BLE restrictions. So think less than 20 bytes, maybe even 16. And because sending is relatively cheap, especially if you're sending the same beacon over and over again, but receiving is not, you might also not be able to measure very often. Now, all of this already, right, even doing the not measure very often and being transmitting in the background all the time required modifications on the operating system level that were not typically accessible to apps, which then means that the big mobile phone operating system manufacturers really need to be involved in order to make this work. And this is what then later led to this Google and Apple exposure notification framework. Now, there are a bunch of other things that, again, led to the same conclusion, namely, obviously these apps needed to be running in the background, which was not possible on iOS at the moment, which means that Apple needed to make modifications. Obviously, also want these apps to be compatible between Android and iOS, which was, for some funny technical reasons, not easily possible. So again, this required cooperation and collaboration with Google and Apple to make work. And then finally, in order for this Bluetooth rotation to work, we actually had to rotate this BLE beacon and Bluetooth MAC addresses at the same time, which again means doing operating system level changes. And so this means that even though the design initially was relatively simple, the fact that we were building on existing platforms really meant, let's say, a more interesting situation, right? So what then Google and Apple did is to say, okay, that is a lot of low-level operating system changes. What we're going to do is build a Google and Apple exposure notification API that will enable this contact tracing functionality. But what it does is expose a high-level interface only. So I made a very crude sketch on the right. This is my mental image of this, right? Their documentation actually has a lot more details. But roughly, if you think about the previous story that I told you, what goes in from the contact tracing apps is a list of these positive identifiers or some keys from which these can be derived. And what the API will send back to the contact tracing app is this user has been exposed or not. So this is really a very high-level API that hides all the details of the contact tracing system. Now, this has a lot of advantages, right? If everybody does the thing that Google and Apple defined that their API does, right? You kind of automatically have interoperability. It also immediately ruled out some of the very scary centralized apps that were out there and were doing very privacy invasive stuff. At the same time, this design choice, right, to push everything to an operating system level API with only high level interfacing rather than potentially lower level interfacing, also really made it difficult to do more privacy friendly choices, right? Like there were choices that we would have maybe liked to do different, or at least the DPTT initially proposed to do different, that we could not do because this was not something that was supported by this API. And this is a story that happens more often, right? When you think about this service-based infrastructure, is that really there's sometimes things that you want to do that you cannot do. This also caused some other problems, right? Is that for privacy reasons, the license terms of this API then meant apps could not use location data. There could also be only one app per nation. Now, a lot of these, right, and I want to be frank with this, right? This caused a lot of positive things in the sense that it really prevented a lot potentially of privacy harms. At the same time, this deployment context in which all of these apps were deployed, right, really meant that the mobile operating system people really had a lot of power over what could or could not be done in ways that maybe nation states or public health authorities did not. Now, the other thing that I want to touch on, one of them, this one already briefly did, right, is that really when you think about privacy, you really need to think about privacy at all layers. I didn't really try to convince you that the high-level design gives you appropriate privacy, but I think if you think about this for a little bit, then yeah, probably this seems to mitigate most of the attacks that you can think about. But once you start thinking about the full layering of all these things, not just the single protocol layer, things really start to become iffy pretty quickly, right? So if you think about these phones, right, these phones are transmitting Bluetooth low energy beacons that I kind of said, okay, they're going to rotate every 10 minutes, right? But underlying this is a Bluetooth stack that will have MAC addresses associated with them. And so this means that if you potentially have an adversary that is listening in, you really need these BLE beacons to rotate at the same time that you're rotating your Bluetooth MAC addresses, because if you don't, you kind of have these things overlapping, and so when one rotates but the other does not, you can still track people along, right? So in order to prevent that, really, you need to rotate them simultaneously, which then required actually OS level changes, was not supported on old phones, but really it speaks to how difficult it is to really get privacy if you're considering the full stack. So just to tell you one other story, right, where again things become tricky. If you think about this part of the protocol, right, where once a user tests positive, they will upload the list of beacons that they have been transmitting. Any network adversary that is able to listen on, let's say, the Wi-Fi network or the internet connection between these users will see that this phone makes this very specifically sized upload to some positivetest.ietf.org upload endpoint, right? Which means that any network adversary that is able to observe this traffic, even if this is TLS encrypted, right, doesn't really matter, will be able to determine medical information about users. And again, this is not a protocol level problem, right? This is a stack or all layers problem that one then needs to go ahead and solve. Now, we did this by letting phones, at least in the Swiss context, right, make dummy uploads that look like real uploads. And they do this kind of regularly in the background following some random distribution, which then gives phones plausible deniability, or rather users plausible deniability, right? Because their phones are doing uploads all the time. And with respect to this network adversary, these things will look the same. Then again, doing so will require background processing that in our case, right, in the case of the contact tracing apps, was actually available, but is not necessarily always available. So zooming out, right, I just want to focus on 3 lessons learned, but if you're interested, there is this communication of ACM paper that goes into a bit more depth and mentions a bunch of others. 3 things, right? First of all, designing with purpose limitation is really important to be able to mitigate all privacy harms. Then the context in which you deploy, right, in this case, mobile platforms, really matters about what you can achieve, and also really matters about who has control over what you can and cannot do. And then finally, when thinking about protocols, right, it is really important to think about all the layers and how to provide protection at all layers, because any of these will potentially be able to invalidate the privacy concerns that you've been able to mitigate. And with that, I'm happy to take questions.
Yeah, Tommy, go ahead.
Tommy Pauly, Apple. So thank you very much for sharing this. Definitely good to kind of hear the whole analysis and these lessons. I definitely agree with all of these lessons. More of a comment than a question. For the kind of the privacy being maintained at all layers, at least on Apple platforms, we also, besides doing random stuff, we are routing it through our private relay, double hop relays for everything, to provide kind of the full IP privacy. So this type of thing also is very good candidate for combining with other things we've talked about in Pair 2 before.
Cool. Thanks, Tommy, for the kind words, right? So just to very quickly jump on this, right? As we know from sort of website fingerprinting, right? Like routing this via VPNs or private relays really helps, in the sense that it will sort of take away the obvious side channel of doing upload.ietf.org with COVID-related stuff, right? But it might still, the size of this interaction or the timings of these interactions might still give away some things, right? So this is like doing VPNs or Tor or whatever is not necessarily enough without also doing dummies, depending on what your threat model is.
Yeah, go ahead.
Hi, Gareth Tyson, HKUST. Thanks for the fantastic presentation. I may have missed this, but I was curious, how do you authenticate that a device is uploading IDs that it itself generated? So for example, if I observe somebody else's random ID and I want to be a bit tricky, would it be possible for me to then upload that and then create false notifications for other people?
What an awesome question. So there are 2 things, right? One is there is typically no binding between the upload authorization as a whole, right? So if I get an upload authorization code, I could, in essentially most systems, I could have given that to you and then you could have done the upload instead. Now, the crypto, though, behind how we are compressing this list of beacons typically means that you need to know the seed from which they were generated rather than the beacons themselves. So you can actually not upload somebody else's beacons easily, right? So you're like under collusion, this would still work, right? Which is just the same as, okay, I just give the key to somebody else, but because you have to know the seed typically in order to do that upload, you cannot sort of pick and match. Now the question is whether uploading somebody else's beacons would do a lot of damage, right? I think the more interesting attack at that point would just be you're trying to broadcast a lot of beacons and do those uploads, and that would be more effective than uploading somebody else's. But that is an interesting question.
Cool. Thanks very much.
Yeah, thanks, Wouter. I had one question on the sort of the integration topic that you mentioned earlier. You were saying that the sort of interface that was exposed was kind of rigid and didn't allow you to use it in ways that you might like in practice, perhaps by tuning different knobs in different ways for different outcomes. I'm wondering if, like, if you could go back in time and, you know, perhaps work with the operating system to provide like different interfaces, what an ideal interface would have looked like for this particular application, and moreover, how might you have constructed the interface in a way that potentially couldn't be misused? So, like, one of the benefits of being quite rigid was that, like, there's not a lot of option to, you know, shoot yourself in the foot. So I'm wondering what your thoughts are on that.
I look, this is very difficult, right? Because I think I will second all of what you just said, right? Like, yes, it was good that it prevented a lot of misuse, but then this rigidity also prevented a lot of cool applications. And so I think, and also prevented more privacy-friendly versions, right? So one potential way that you could have done this is to have a much more lightweight interface that would essentially have exposed beacons, for example, and so have pushed a lot of things onto the app, and then to use other processes to potentially prevent these harms. Right now, I'm not saying that any of these are ideal, right? Like it is sort of like a little bit of a golden cage story, right? Like this oversight process that was in place, right, was in many ways very rigid. It probably prevented a lot of harm, but it might also have done harm by being there. And as with always these things, I don't think there is an easy, unfortunately, there is not an easy answer.
Yeah, for sure. I don't mean to suggest there is a correct answer. It is, at the end of the day, a pile of trade-offs, and I'm just wondering how you thought about those trade-offs after having been on the other side of this particular project. But anyways, thank you very much. I think in the interest of time now, we'll move on to the final presentation, which will be given by Alexandra. I don't know if she is here or remote. Okay,
Hey.
remote. Hello.
Hope you can hear me.
Yes, we can hear you fine. It looks like you've requested to share your screen.
Exactly.
It's perhaps simpler if you just request to share your slides.
Okay.
Oh.
We can.
No. Sorry, go ahead, Shravan.
No, I think, do you have access now? Yeah, cool.
Sorry.
Yeah, we can see your slides. I think you're good to go.
All right. Okay. Give me a second. Okay, so you can hear me, right?
Yes.
Okay, great. Yeah, thanks for having me. My name is Alex. I'm from Germany to Braunschweig, and I'm a fellow at Sensor Planet. So today I want to introduce you our paper that's called Lockpicker, Strengthening Certificate Transparency Against Covert Adversaries. So something completely different. It was published 21 at PETS. Okay, now let's start. Yes, so HTTPS is kind of a default nowadays, we could say, because I think last month about 96% of all page loads in Chrome were served using HTTPS. So we can kind of see it as being a default. And the certificates that are needed for HTTPS in the handshake are issued with certificate authorities. So the certificates are used to bind a domain to a public key or to a specific public key, so to the domain's owner. So we can say that certificate authorities, or CAs, are kind of a trust anchor of the web PKI. And guidelines on how exactly certificates should be issued and the whole procedure and the acceptance of browsers of a certificate authorities are mostly discussed in the CA browser forum. So consequently, the number of illicit certificate creations is increasing, of course. So just to give you a short overview, these are some certificate authorities that are known for some illicit certificate creations, like WuSign, it's this here. They created certificates that were backdated or did not report known incidents, or like Turk Trust. quite critical one. They created an intermediate certificate instead of a regular one, which is crucial because the intermediates are able to create further certificates or sign further certificates. Or let's say the Malaysian DigiCert, they issued certificates with weak cryptographic keys. So the list of such kind of incidents is quite long and quite old. However, all of these issues were mostly of technical nature. That means there are security vulnerabilities or some infrastructural vulnerabilities that leads to this illicit certificate creations, probably. Okay, but let's assume a quite strong attacking model, which tries, or a strong attacker that tries to obtain a rogue certificate. A rogue certificate is one that you obtain for a domain that you do not own. So this is what we call the rogue certificate. This kind of attack is called HTTPS interception, and a government, which I would assume to be quite a strong attacker because they have a lot of resources, there are attempts from different governments who try to make HTTPS interceptions legal. Like, I think most of you know the case of Kazakhstan, or last year Mauritius also tried to make it legal to make HTTPS interception attacks. So most of those states are, let's say, states with a weaker commitment to democracy. So the browser vendors in this cases took action to protect their users by, for example, blocking the government-based certificates. But the question is, why should the attacker stop at this point? If it's not possible to do it on a legal way, and the attacker is quite a strong attacker, so they have a lot of resources, why should they stop here? Okay, so let's get back to the attacking model. In 2007, Aumann and Lindell introduced the covert adversary attacking model. So this is anywhere between a malicious attacker and a semi-honest or honest but curious attacking model. A malicious attacker, he behaves completely arbitrary, is not bound to a protocol, while the semi-honest model follows the protocol but is quite curious and tries to obtain as many data as possible. So the covert adversary is anywhere between those two models, and the goal is to obtain data and to attack only if the attack remains undetected, even after the past. So the next one is the compelled certificate creation. This is an attacking scenario that was introduced in 2010. So we have a really strong attacker in this model, or in this scenario, who is able to compel a certificate authority to omit the ownership check. And the ownership check is what CAs have to do before issuing a certificate for a domain. So they have to ensure that the domain belongs really to you. Okay, so get back to our scenario. We have a really strong attacker who only succeeds if he is able to create a rogue certificate for a domain and the attack remains unnoticed by the legitimate domain owner. Okay, so the mitigation for this kind of attack, the pre-work began 2012 by Ben Lowry et al., was called public certificate creation. And the goal was to force the certificate authorities to publish all certificate issuances in any public way. So a really, really short primer on certificate transparency. Let's say this is the infrastructure. We have a domain owner on this side, and we have a certificate authority on this side. So the certificate authority issues a certificate in behalf of the domain owner, which is the red one here. And the certificate authority wants this certificate to be accepted by each CT-capable browser, of course. So it needs to publish the certificate to any kind of log. That means it sends the certificates to one or more favorable logs. And after that, now it needs a proof for this process. So the log sends back something that is called an SCT. We can say this is kind of a signed promise from the log to the CA that the certificate will be included in the log's Merkle tree. This is how the logs are working. In its Merkle tree within the next 24 hours. So now the CA can just send back to the domain owner the new certificate and the proof. And the domain owner can kind of develop the website using HTTPS with the certificate and the SCT. So, and CT also introduces two additional parties. The first one are the auditors. The auditors are mostly third parties. And their goal is to check whether all the logs comply with the requirements of the CAB forum. That means something like the uptime and complying with the SCT that the logs send it and stuff like this. So it's not domain dependent. And the monitors on this side, these are also mostly opt-in services or third-party services, mostly by CAs. Their goal is just to, in behalf of a domain owner, check all the logs for exactly this one domain, whether there are some rogue certificates existing. So the monitoring service is domain dependent, and the monitors and the auditors are not communicating with each other. Okay, so we claim that certificate transparency is still vulnerable, and also after the paper was published 2021, we claim this is still the case because until today's date, there are about 30 or 40 certificate transparency logs that are usable or acceptable by browsers, mostly in Chrome, of course. And all of those logs belongs to other CAs or to the same vendors. So we can assume that attacking a CA or controlling a CA is equal to attacking or controlling one or multiple logs of the CA. And most of the CAs has multiple logs. And the first compromise of a log, I think, was in 2020. It was a salt vulnerability, so it was a technical vulnerability compromise. But, well, this shows that, yes, logs are same vulnerable as CAs as well. And the other vulnerabilities followed after that. Yes, and the collaboration attack, which can be, or which is the attack that we talked about previously. So this attack from a covert adversary, omitting a CA or forcing a CA to omit the ownership check, is also defined in the CT threat model. So the RFC exactly defined this threat model and still state this problem to be an open problem and not solved today, until today. Of course, we can say, oh my God, you need a really strong attacker for that because you need someone who's able to control some part of the subnetwork and its country for conducting HTTPS interception. But again, we are talking about strong attacker like a government. And especially today, there are a lot of governments who could possibly be able to do that. So there was some work from this year in 2008 who explained this kind of attacks to have a really low probability because it's hard to conduct them, but a quite high impact because you're able to make HTTPS interception on a whole country or a specific subnetwork of a country. So one of the possibilities could be, if you obtain this kind of rogue certificates, is to create a split view attack. So probably most of you remember split views from this blockchain thing back then. A really short primer about split views. A log is a Merkle tree, and the log can create two different views of its own Merkle tree. So this one view here is the view that would be served to a monitoring service. And the red certificate, which our CA created previous, is not included in this view. That means the monitor, who is watching for rogue certificates in behalf of the real domain owner, cannot see any kind of attack because, well, there's no rogue certificate. On the other hand, the malicious log can create a second view, which is served to the auditors, because the auditors know about the SCT, about the signed certificate timestamp promise, and the red certificate is included in the stream. So the auditors who only check the technical compliance with the requirements, they see, okay, there is the red certificate, everything's fine, and they don't know who the domain owner of the possible rogue certificate are. So there is no attack for them. Okay, so this is something with the split view. A quick reminder how our certificate transparency infrastructure looks like. And there was a mitigation attempt for exactly this kind of attack, which is called gossip. Well, gossip is really complicated. So I don't want to go too much into detail, but gossip involves anyhow almost each participant in this whole certificate transparency infrastructure. So also the client of the user and also the web service. So the clients collect the SCTs and send the SCTs back to other parties of this infrastructure. and by the way, breach a lot of their browsing history this way. This is one of the most critical points on gossip, and because it's really complicated. So all the participants are communicating with each other, and this way, of course, the auditors and the monitors know about which kind of SCTs are in this infrastructure. But well, gossip is a draft since 2015. And even if the certificate transparency RFC requires all the participants in this infrastructure to gossip, the RFC of gossip is expired since 2018, well, because it's not really feasible in the way the internet or the web PKI works at the moment. So the question is, why can't we just, I don't know, introduce any further trusted parties who are doing any kind of auditing or whatever? Well, because it's not working, you cannot just shift the trust from one party who could become malicious to another party. It's not working. And one of the inventors of CTU, Ben Lowry, also said that fixing one set of trusted parties by introducing another doesn't seem to be a step forward, and I would really agree to that. Okay, so Lockpicker. We thought about how to think of some kind of another approach to this issue, and what kind of goals do we need to that, or kind of an extension for certificate transparency or whatever. So at the beginning, we just talk about the desiderata. We had some security goals in advance, which first off was, of course, mitigation for this kind of collaboration attack for one malicious CA and one or possible more malicious CT logs. The next one, we wanted to have more witnesses in the whole certificate issuance process. And oh, by the way, we also count that the publication of the certificate in the log is also part of the certificate issuance process. So we counted that. So in this malicious case, only the malicious CA and the malicious CT logs and possibly the rogue attacker knows about the existence of this certificate for the beginning. So we wanted to involve more witnesses on an automatic way from the beginning. And of course, everyone, also the witnesses, should be able to prove that this certificate exists, and not only the possibly malicious parties. And well, monitoring, the first critic is this is still an opt-in service, so it's mostly used by higher level domains like Google and Facebook and stuff. And monitoring also just happens after the fact, after the certificate was possibly issued. So we wanted to be able anyhow to involve monitoring service on an earlier state of the issuance process. And further, we have some design goals. The first one, of course, we don't want any user data, like the browser history of the user, to involve in this protocol, like it's the case of gossip. The next one is we don't want the web servers who serves the websites to need to change anything on their default behavior, because, well, we know that they are not good at adopting new changes on the web. So incremental deployability. I think this is one of the reasons of the success of certificate transparency, because they had no kind of flag day, which means that each web server has to change their behavior like from tomorrow, because the new changes will take place. So it's kind of incremental process to deploy the new protocol. And we don't want any new and trusted entities, because the whole system is completely complex. Of course, it looks quite easy on my slides, but it's horrible complex. So we don't want to include any new entities to the whole process. So again, a quick reminder on how the infrastructure on CT looks like at the moment. And this is where we end up. So the first changes maybe that you can see is this clustering and this petrol LPP. So the clustering, instead of the certificate authority contacting its favorable logs, instead it contacts one specific log from a list of logs. The log can also be malicious, it doesn't matter. So the logs and on this list are the logs that the browser is trusting. So this is at the moment also the CT policy, which exactly defines which logs are trusted, so from which logs the browser accepts as CTs. So our CA contacts one log out of these logs, and the other logs form together something like we call a log pool. So exactly. And the other one is the proof, which I will explain in detail. What you maybe also can see that the auditing service is missing here. I will come to that later. Okay, so in the first step, our CA chooses the leader log. Doesn't matter who this is, just one log from the list. It also can be its collaborating malicious log. It doesn't matter. And on the second step, this leader contacts the whole log pool. Because the CT list of the browser is public, the leader log also know which other logs are on this list, and these all together, they form kind of a log pool. So the leader contacts each other participant of this pool, and from this on, kind of a 3-round protocol happens. That means that the pool collaboratively select one log of this pool by random. This is a randomness protocol. Yes, so at least one honest log is among all this pool. The randomness is true. That means from this point on, neither the CA nor the possibly malicious leader log can influence the log selection. And the one log that is selected from all of the logs is in charge of including the certificate in its Merkle tree. So at this point, the chance to get a malicious log being in charge to include a certificate is really, really low for a possibly malicious CA or possibly malicious log.
Alexander, just a time check. You have about 5 more minutes, five or 6.
Yeah. I can see that. Okay, so and from this point on, each log who participated in this protocol round can sign kind of a proof, and all the proofs are aggregated and attached to the certificate. This is what we call the LPP. So this is an aggregated signature, which also kind of includes the proof from each witness who participated, and can also be attached to the current data, which is the certificate in the SCT. All this stuff is sent back to the CA, and the CA sends this back to the user, which can then kind of deploy their website using this new material on the same way as this happened like at the moment. So, well, on the Rust side, the achievements by randomly selection of the log. This is a mitigation for the malicious attack we talked about earlier. We have a lot of witnesses, and the witnesses can also prove their participation, and they can also prove who was selected in this round for including the certificate. And up from the second round, when each of the logs gets the request by the leader log, hey, we want to make a log picker round for some specific domain. At this point, from this point, the logs could also contact any kind of monitoring service, like, hey, there was an attempt to create a certificate for your domain, just in case you're interested. Well, we have no user data involved because nothing changed regarding the data. The web servers don't need to change anything because it's the same like in CT. The web servers just get this material from the CA, and they don't care about, is this a log picker proof, is this an SCT or a certificate, whatever. So nothing changed. And the same for the incremental deployability. It's also the same way like in CT, because the browsers can kind of deploy this transition phase when log picker would be like optional or would be mandatory. And we have no new or trusted entities in addition, because the logs are trusted anyway by the browsers. So they have this pool. Exactly. And we don't have even auditors, because the logs can make the auditing service themselves. And well, in the paper, we have some additional things, like we have a lot of cryptographic primitives, which are explained, and the protocol goals, and of course, the analysis of our achievements. We have a probabilistic analysis of the correctness of what we call the LP-based PKI, the CT-based PKI, and the gossip and CA-based PKI with a comparison. And then we are discussing the certificate transparency policies and what should be changed for log picker. We also have a prototype simulation of a possible log picker based PKI. Well, and to get to my point, of course, the outlook is we have to think about how and when could we include the monitoring service. The interlog auditing, which is a kind of important thing, because the logs know that a certificate was issued. So they could automatically, after 24 hours, make the auditing service by themselves, because they know which log is in charge of including the certificate. So how can we include this process afterwards? Of course, we have a lot of protocol boards and we need to think about how to handle it. And well, revocation of certificate is horrible still. So maybe it's possible anyhow to include revocation of certificate in log picker protocol. Okay, so thank you for your question and I'm for attention and I'm open to questions.
Yeah, thanks. We're really short on time. I do have a question, but I wanted to give someone else the opportunity to ask a question just in case. Okay, if not, so I guess first a clarifying question. So the way I understand this design, you effectively, from this pool of logs, you basically run some like election protocol of sorts to like pick a random log effectively to sign the thing. And that's how you work around a potentially like malicious log, otherwise like trying to subvert the system. Is that correct?
Yeah, exactly. We just have a 3-round leader election protocol and the randomness protocol combination to ensure that neither the malicious log, possible malicious leader log, or a malicious CA can influence the selection of which log is in charge of including the certificate in its Merkle tree.
Okay. I'm wondering if you looked at like perhaps alternative solutions that were based on like threshold like crypto systems. So for example, say rather than just signing by one log, you just require that, you know, some threshold number of logs sign, and then under like perhaps a quite reasonable assumption that not all of these randomly chosen logs were colluding, that the system would have the desired properties. That might require other, you know, ecosystem changes, of course, because like this is a different type of signature, but I'm wondering if you looked at that as an alternative design.
Yes, the signature that we're using at the end for the certificate proof by the witnesses. At the moment, like just for the paper, we took BLS multi-signatures, but we also discussed in the paper that we need to take a look on how exactly or which kind of signature should be built at this point. So the cryptographic technique behind whether this is a threshold signature or a BLS signature, it doesn't really matter because the protocols themselves, the leader election phase is important. So the signature which comes out at the end, this could also be a threshold signature. I know that my co-author, who is more of the cryptographic guy, he was also discussing to a lot of people about threshold signatures, but these are the details, which cryptography to use, because the paper is kind of a like an abstract view on how this kind of protocol could be made. And yeah, cryptographic details should be the next step probably.
Understood. Thank you so much. Unfortunately, we're out of time. This is the end of the session. So thank you again for coming and presenting, and thank you to everyone who joined us. Yeah, and thanks to Matt for taking notes. Appreciate it.
Thanks especially to our European presenters. Like it's pretty early for them, so thanks both of you. And I think if anyone's working on certificate transparency, I'm sure Alexandra would love to talk to you. See you all next time.
I need